Hi folks, welcome to this video on the Chapter 8 assignment prep solutions, or the review solutions. You can find a copy of the review with all the work solutions in the video description below. And honestly, that might be a quicker way to troubleshoot some areas than actually watching this video. That said, each of the questions are time-stamped in the video description, so you can skip to where you need to get to. Make sure that you actually try the questions first, though, because it won't be that helpful to just watch me do them. Okay, with those caveats out of the way, let's give this a go. So we have some non-calculator stuff to begin with, and we're asking what's the log base 3 of 9? So it's saying 3 to the power of what gives us 9? In other words, 3 to the question mark equals 9. The answer to that is 2, the missing exponent here. So the log base 3 of 9 is 2. It's not 3 squared, it's not 9, it is the missing exponent of 2. Let's keep going with that idea. So I have the log base 4 of a quarter. Again, this is just saying 4 to the power of what gives me a quarter. Now remember, negative exponents flip. So 4 to the negative 1 equals a quarter. That's the thinking we do. And that means that the missing exponent here was negative 1. The log base 4 of a quarter is negative 1. The next one says log base 5 of 1. So again, we're saying 5 to the power of what gives us 1. The answer to that is that 5 to the power of 0 gives us 1. So the missing exponent here would have been 0. That's our answer. Log base 6 of 6, similarly is saying 6 to the power of what gives us 6. This one's pretty easy. Hey, that's just 1. 6 to the power of 1 gives you 6. The next one's a little bit trickier. It's saying 8 to the power of what gives us 2. So how can we use powers to turn an 8 into a 2? One thing that I know is that the cube root of 8 is 2. And a cube root is a power of a third. So 8 to the 1/3 equals 2. Those are all the pieces of thinking that you might do. But the final answer here is that the missing power is 1/3. Just as an off to the side here, let's just recall that ln of e, if you see natural logs, the base is automatically e. So this is asking e to the power of what gives us e. Ln e is 1. Similarly, if I had something like ln e squared, it would be saying e to the power of what gives me e squared. Okay, anytime we have natural logarithm, or ln, then the base is e. So the answer to this, obviously, would be 2. E to the 2 equals e to the 2. So we could also have some natural log stuff happening. All right, next question. Convert to a single log, then evaluate. So this is asking us to use our log laws. And one of our log laws is this. Log A minus log B is the same thing as log of A over B. That's the quotient rule of logs. So this is going to give us, as a single log, log of 3,000 over 3, or log of 1,000. Whenever there's no base shown, the base is assumed to be 10. So let's go to Dreamland again. This is really just asking us, 10 to the power of what gives me 1,000? And the answer to that question is 3. 10 to the 3 is 1,000. So in the end, this whole expression just meant the number 3. Let's take a look at another one. We've got 2 log base 3 of 6 plus log base 3 of a quarter. So here we've got some issues. I don't know what the log base 3 of a quarter or 6 is, but I've got a couple of log laws that I can use. One of them is this. If I have n log a, that is the same as log a to the n. This can live up, the n can live as an exponent up top. And this will work for any log base. I'm writing it with just a base 10 here, but it would also work with a base 3 like we've got in this question. Another log law that we know is this one. Log A plus log B equals log of AB. That's the product law. So between those two things, we can start to simplify this. This really means the log base 3 of 6 squared plus the log base 3 of a quarter. Okay, now 6 squared is 36, so this is log base 3 of 36 plus log base 3 of a quarter. Okay, I don't know the log base 3 of 36, but I can use that product law and put them together. So this is really 36 times a quarter when I put them together using this law over here. And some of you might immediately evaluate that as log base 3 of 36 times a quarter is just 9. And now let's go to dreamland. It's saying 3 to the power of what gives us 9? And the answer to that is 2. So this whole expression was just secretly saying 2. Find the equation of the inverse. So when you're finding the equation of the inverse, the first thing that you do is switch x and y. So I'll get x equals 3 to the y. One easy way to get that y out from the exponent is to go to log form. So use log form. It's not the only way. You could take the log of both sides, but I like this idea. So in log form, we go log of base, then the answer from exponential form, and it will equal the exponent from exponential form. Let's see, the base is pretty easy to figure out. It's this 3. So we're talking about log base 3 of, the exponent was y, so let me put that here. And then the answer in exponential form was x. I always figure out my base and then my exponent, and by process of elimination, I've got the last piece of the puzzle. So the inverse of this y equals 3 to the x is y equals log base 3 of x. If you graph them together, they will look like inverses of each other. All right, the next question asks us to rewrite some expressions in terms of log a, log b, and log c. So here I've got an a squared b all over c to the 5. What I notice first is that there's division. And I like to do these questions in multiple steps. I'll just notice that there's division, or a quotient, and I know I can split that up as the difference of logs. That's one of our log laws. Next thing I'll notice is that there's multiplication here. So those can be split up as the sum of logs. That's our product rule. And if you need a refresher on any of these actual techniques, there is a link to the Chapter 8 Concept Roundup video down below. Lastly, I might notice that I can bring my exponents down front, because it is asking for these things in terms of log a, b, and c, not log a squared. So this will become 2 log a plus log b minus 5 log c. Here's another one. Log of a times the cube root of c to the 5. Okay, so first thing that I notice is that I've got a product here. So I've got log of a, that's not a cubed, it's log a times the cube root of. Log of the cube root of c to the 5th. Okay, let's keep on going with this. So that's log a plus the log of. A cube root is just a power of a third. So this is c to the 5 to the 1/3. I can still make that a little nicer. If I have powers to powers, then I can multiply these powers together. 5 times 1/3 is 5/3. So I have c to the 5/3. And lastly, I can bring that exponent down front using my power rule. So I get 5/3 log c. Last question here. We're asked to do an exponential equation, but we don't have logarithms to play with. So let's take a look at what we could do here. If you don't have logs, you can look for a common base. And when I see the numbers 9 and 1/3, I think about the number 3 as a common base. Now, how am I going to rewrite this? I've got something to the 2x minus 1. That something is 9. I'm going to rewrite 9 as 3 squared, because 9 is 3 squared. And then on the other side, I have something to the x minus 3. Now that thing is 1/3, which I can also write as 3 to the negative 1. So I haven't changed the value of any of these terms. I've just changed the way they look. I wrote a 9 as 3 squared, which is fair, and 1/3 is 3 to the negative 1, which also is fair. What that lets us do next is break out of our exponents through multiplication. So we have powers to powers, so we multiply those powers. So I have 3 to the 4x minus 2. On the other side, I have 3 to the negative x, careful here, plus 3. And now we can drop our bases because we're saying that 3 to the power of something is equal to 3 to the power of another thing. That means the exponents themselves must be equal. Drop bases. So now I have 4x minus 2 equals negative x plus 3. Let me bring those x's over. I'd have 5x equals 5, or x equals 1. And you could go and throw them back in and see what happens. If I put in 1, I'll have 9 to the 2 times 1 minus 1. So on the left side, I'd have 9. On the right side, I'd have 1/3 to the power of 1 minus 3, which is negative 2. And negative 2 as a power just tells you to flip and square. If you flip and square 1/3, you get 9. So the left side equals the right side. Yay! Our solution was okay. We didn't have to check it, but it makes us feel better to know that it is indeed correct. Okay, moving on to the section that allows us to use the calculator, we're going to do some graphs. And honestly, I don't think you need the calculator here. You may on some of the later questions. So right here, I know that I have an x-axis reflection. I know that I have a vertical stretch by a factor of 2, stretch x2. And I know that it has gone up 4. None of those things actually affect my asymptote. My asymptote's still on the y-axis. So here's the map that comes out of that. I've got an x-axis reflection, so that changes my y's to negative. And I times my y's by 2 because it's a vertical stretch by a factor of 2. And I go up 4. The x actually hasn't been transformed at all. Here comes the key points. 1, 0 is an easy point to use on every log graph. And the other one we're going to use deals with this base over here of 3. So it's going to be 3, because 3 is the base, 1. Let's see how these get transformed. So this will turn into 1. Negative 2 times 0 plus 4 is just 4. And this other one's going to turn into 3. And then 1 times negative 2 is negative 2 plus 4 makes 2. Now I can plot these points. So 1, 2, 3. I have a point 1, 4. There we go. And I've got a point 3, 2. Now all I have to do is make the graph. And it's got a vertical asymptote, not a horizontal one. So it is going to, some point, go through that x-axis. I don't know exactly where. But it's never going to travel through the y-axis because it's a logarithmic function. It has a vertical asymptote. Let's do another one. So in this one, we have a horizontal stretch by a factor of 2 because it's got a half there. And we've moved left 3. Okay. That is a change to the asymptote. The asymptote that is usually on the y-axis has now been moved 1, 2, 3 to the left. I'm going to do that before I actually draw in any of the points because I know I might forget my asymptote. All right, let's make a mapping rule. So xy is going to get turned into horizontal stretch by a factor of 2, so that's 2x. Left 3 means we subtract 3 from our x value, and nothing happens to the y. The key points, they're always going to be 1, 0, and again, we're going to use this base, so it will be the point 4, 1. Let's transform all of this. So 2 times 1 is 2, minus 3 is negative 1, and 0. And the other one's going to be 2 times 4 is 8, minus 3 makes 5, 1. Okay, let me go and plot those points. Negative 1, 0. 1, 2, 3, 4, 5, 1. There we go. There's our other point. And because they're integers, I didn't bother to label them. If they had been fractions, I probably would have, because I would have been nervous that my teacher wouldn't know exactly where they are. Okay, and there we go. We've got them sketched. I didn't do a perfect job. The iPad is a little unforgiving sometimes. There we go. That looks a little better. And that's the technique. Map a couple of points. Okay, now we're on to solving some equations. So we are going to try and isolate our exponential term to begin with. So I'm going to divide both sides by 3 here. So I have 2 to the 5x equals 9. Obviously, I can't find a common base here. All that I can do is take the log of both sides, though that's not the only technique we could use. So I'm just going to write log in front of both sides, because that's fair. As long as you do the same thing to each side, then it's still balanced. And at that point, I can bring my 5x down. And I want to get x on its own. Now, some of you are going to feel comfortable dividing by 5 log x. Some of you are going to feel comfortable dividing by 5 log 2 all at once. I'm just going to divide by log 2 because I'm nervous that I'll botch it in my calculator. Okay. So after this, I'll have 5x equals something, and that something, let's see, was log of 9 divided by log 2. Okay, we get 3.17 or 1699. 0.1699. I could keep more decimal places. Now I know the final step is just divide that by 5. Okay, so I'll go back to my calculator, and I'll just take that answer that's already there and divide it by 5. I get 0.634 to 3 sig figs, which is kind of what we'll be aiming for. The next one is significantly nastier because it has x's on both sides. So again, all we can really do is just take the log of each side. 4 to the x minus 1 equals the log of 5 to the 3x plus 2. At this point, I'm just going to pull my logs down front. So I'll have x minus 1 log 4. Notice those brackets because it's the whole exponent times the logarithm of 4 and 5 respectively. Okay, at this point, if you divide by log 4 or log 5, you'll probably just create a different kind of mess for yourself. You could also go to decimals and figure out what log 4 and log 5 are as decimals and then work that way. But probably the slickest way to do this is to expand out. So what will we get on the left? We'll get x log 4 minus log 4. On the right, we'll get 3x log 5 plus 2 log 5. Next thing we're going to do is collect x terms on one side. On one side. Let's see what happens. So I'm going to keep my x log 4 here. I'm going to move this one over, so I'll have minus 3x log 5. On my other side, I'll keep the 2 log 5, and I'll also move over this log 4, so I have plus log 4. Could you have done it with the x's on the other side? Absolutely. And here's the trick. You're going to factor out x. X is a common factor on the left side, so if we take x out of each of these terms, we're left with log 4 and 3 log 5. Equals 2 log 5 plus log 4. All right, at this point, we're just going to divide. So I'll divide this whole thing by log 4 minus 3 log 5. And if you have a fancy calculator, you can probably put it in as is. If not, then make sure that you're putting brackets around the tops and bottoms of everything. So I'll head to the calculator here. And again, if we can put it in nicely, then it works out great. So I'll have 2 log 5 plus log 4 all over log 4 minus 3 log 5. You can put these together with log laws if you wanted to. Okay, we get this, negative 1.34. If you put it in all together, and you don't have a fancy calculator, then you need to start by opening some brackets. Then close them for the top. And then divide by the bottom. And the bottom needs to start by opening some brackets. So it is doable, but it's no fun. Okay, brackets are all closed, fingers crossed, same answer. Another thing that you can do is just figure out the top as a decimal. Oh, that's pretty nice. Figure out the bottom as a decimal. Log 4 minus 3 log 5. Okay. And then just divide those two out. 2 divided by negative 1.49485. I think it'll probably be close enough now. Still get negative 1.34 to 3 sig figs. So a few approaches there. If you have a nice calculator, you're kind of spared from all this misery. Any way we slice it, we should end up with negative 1.34. Moving on to the log equations. If only some of the terms are logarithms, then I think you should switch to exponential form. So I'd be thinking bay here. I'd rewrite this as 2 to the 5 equals x. Oh my gosh, 2 to the 5, that's no big deal. That's 32. And we should always check to make sure it doesn't cause us to break the law. If I put in x equals 32, I'm going to get log base 2 of 32. I'm wondering if it's 5, but really mostly I'm wondering is this okay to have the log base 2 of 32? Absolutely. You're not allowed to take the logs of 0 or a negative, but you can take the log of a positive. Similarly, in the next one, I can move that 3 over. You can see right here that this 3 is causing us grief. So we'd have log base x of 4. Just trying to isolate my weirdest thing. And then we'll switch to exponential form. Okay, so we get x to the 2 equals 4. Now normally that would give us plus or minus 2. Right? But if I check each of those, let's see, check x equals 2, log base x 3 plus log base 2 of 4, we're wondering is that 5? The main thing is that this over here is okay. If we check x equals negative 2, we're not too happy about having a negative base. So we've been using only positive bases, and we would say that this is not okay. Can't take the log of 0 or a negative, and we don't use negative bases. So what we're going to say here is that the answer, final answer, should just be 2, just the positive 2. We can write a couple little notes here. Only take logs of positives. Logs of positives. Only use positive bases. All right, the next one that we have is comprised of a bunch of log expressions. So we can use log laws to put them together. They're all the same base. I can use quotient law to rewrite this as a single logarithm. And here you don't have to switch to exponential form, because we just have log base 2 of something equals log base 2 of something else. We can drop the log terms here. So that gives us x plus 3 over x plus 7 equals 4. That looks a little bit miserable, but we can deal with the fractions fairly easily. Just times both sides by x plus 7. That'll cross them out on the left. We'll get x plus 3 equals 4x plus 28. I go around and I rewrite this. I'm going to move my numbers to the left side. So I'll have negative 25 and then 3x here. Or x is negative 25 over 3. At that point, I do need to go and check. So check x equals negative 25 over 3. So when I put it in, I'll have log base 3, or log base 2, sorry, of negative 25 over 3 plus 3. Now, I can tell you that this is going to be a negative number, so it is not okay. We can't take the log of a negative. We've got it right over here. Only take logs of positives. So this one possible solution we found did not work. So I'm going to cross it out, and I'm going to write really clearly for my teacher, no solution. The only candidate for a solution we found didn't work. All right, this next one, I'll show you two different ways of approaching it. It looks kind of like the last one because it's comprised of log terms on both sides. The problem is this pesky 2. So one way you can deal with it is putting it up as a power over here. I'll zoom in a little bit. So that'll give me log of x plus 1 all squared equals log 9. Now I can drop the logs because it's log equals log. And I get this. All right, that's a quadratic. Now, if you want, you can square root at this point. That might be really slick. Some other people are going to expand it out. Either way, you're going to get the same answer. Or perhaps you're going to use quadratic formula later on. So I'm just going to expand it out, even though it maybe isn't the slickest technique at this point. And once I get it in trinomial form, I'll make one side 0. Then I'll factor it. I'm looking for numbers that add to 2 and multiply to negative 8. Those two numbers are 4 and negative 2. So I have x plus 4 by x minus 2 equals 0. And solutions, potential solutions, of negative 4 and 2. I need to check those out. If I put negative 4 back in here, I'll have the log of negative 4 plus 1, which is the log of negative 3. That's not okay. You can't take the log of a negative number. On the other hand, if I put 2 back in over here, I'll have the log of 2 plus 1, which is 3. That's fine. So this is our single solution here. Even though we found two potential ones, only one worked. And the name for this is an extraneous root. Okay, here's another way that you could approach this. You could have multiplied both sides by a half, and that would have given you just log of x plus 1 on the left-hand side, and a half log of 9 on the other side. And then that would have given us, let's see, that half could live up top as an exponent. And 9 to the half is just 3. Now we can drop our logs. X plus 1 equals 3, or x equals 2. We already checked it out. It's fine. If we use this second technique, we never turn it into a quadratic, so we never see that extraneous root. Which way is correct? They're both fine. Are there more ways that you could do it? Absolutely. And on that note, this last one also has a bunch of approaches. The way that I like to do it is to turn it into what I call a short log equation, and that's to get all my logs on one side. You don't have to do it this way, though, but that's what I'd like to do. So on the other side, I have log base 2 of x plus 1, and I'm moving over the other log. So I have 3 equals log base 2 of, put them together with the quotient rule, or quotient law, I get this. Now I can put it into exponential form. We might get confused because the log is on the right-hand side, so you could always just flip it around. And now I can more easily think about bay. So I'll have 2 to the 3 equals x plus 1 all over 3x minus 1. We're still not done, but at least we're a little closer. Okay, at this point, maybe I'll figure out what 2 to the 3 is. That's 8. X plus 1 over 3x minus 1. And now I can just times both sides by 3x minus 1. And let's see what that gives us. First of all, we cross them out on the right. On the left, we'd have 24x minus 8. On the right, we'd have x plus 1. We could move things around. We'd get 23x equals 9. Or x equals 9/23. All right, now I have to actually go and throw that back in and see if it's okay. Now, it's a positive number, so it's going to be fine over here, because 9/23 plus 1 is still positive. You might wonder with this one, is it going to work out? So 3 times 9/23 would be 27/23. Minus 1 will still be positive. So this is okay. All right, the last big topic on this review is about word problems. So I have this funny little equation that I like to write this way, where PO is the initial amount, C is the growth or decay factor, time is T is time elapsed or time passed, and smiley face is the amount of time for one specified change. So this review sheet's a few years old. It's probably about 5 years old. And it's based on this idea. This question's based on this idea that storage capacity doubles roughly every 18 months. So at that time, the maximum storage capacity of an SD memory card was about 128 gigabytes. Find the maximum storage in 5 years. I mean, that's probably today. So let's see if it holds up. It's expected to double. That means C is 2. Gets 2 times as big. And how long does it take for one of those changes of doubling? Takes 18 months. So smiley face is 18 months. Current maximum storage is 128 gigabytes. That's our PO. Find the maximum storage in 5 years. Aha, this is our T. T is 5 years. But notice that smiley face was in months, so we probably should write this in months too. So this would be 60 months, just 5 times 12. All right, we're ready to go here. So we'd have P equals PO C to the T over smiley face, or P equals 128 2 to the 60 over 18. Let me head to my calculator. 128, 2 to the power of. I'm going to be paranoid here and put in some extra brackets. My calculator's all right without them, though yours may not be. So there we go. Let's see what it says. 1290. It's really not far off. There's no allowing for the fact that we now have micro SD cards, but a little over a terabyte. How long will it take for the maximum storage to exceed 300 gigabytes? So really we're wondering, we've got this kind of set up. We don't know how long the time is, and we're wondering whether that's going to get to be bigger than 300. Now probably the easiest way to solve this is to consider it as an equation, even though we're wondering about exceeding. But when will it meet 300 gigabytes? All right, so now we've got an exponential equation. The unknown is up there in the exponent, So that means we're going to have to use logs later on. Let's start just by isolating the exponential term. So you can leave that as 300 over 128 if you want. I think I may do that, 300 over 128. Or you can figure it out as a decimal. That's fine either way. 2 to the t over 18. Okay. So now we're thinking, I got to get t on its own. It's stuck up there in the exponent. Only way to do that is to log both sides. And again, if you're finding this fraction weird, well, just write it as a decimal with a bunch of decimal places. Okay, now I can pull down that exponent, which is the great gift of logarithms. And I can start to work on getting t on its own. If it were me, I'd do it in 2 steps. I'd divide by log 2. And then I'm going to know what t over 18 equals. So let me throw that in my calculator, the left side. Log of, oh, it nicely opens some brackets for me. Log of 300 over 128. On your calculator, you may need to open the brackets yourself. Divided by the log of 2. Get 1.2288. I think I can remember that. 1.2288. Now what do I need to do to both sides to get t on its own? I need to times by 18. So let's go back to the calculator. And we'll do that. We'll multiply by 18. We get about 22 months. 22.1. And remember, since our smiley face was in months, this time is also in months. For compound interest, t will always be in years, but for other questions, it can vary. Okay. So I would take as a final answer either about 22 months, or if you wanted to go one higher, because it doesn't exactly happen at the 22-month mark, or 23 months would be okay too. All right, next one. The population of a small town is currently 11,000. It's decreasing at a rate of 6% per year. Let's figure this out. It's currently 11,000. That's PO. Decreasing at 6%. So it's 100% of what you had to begin with minus 6%. In other words, every year there's 94% of the population left, or really you're just multiplying by 0.94. That's what C is. When they say per year, that means that 6% change happens every year. That's smiley face. And it's 1. Find the population in 8 years. So here they're telling us T is 8. So smiley face is 1, T is 8. Let's plug this in. I've got my full service formula. It'll do me for pretty much every exponential application. 0.94 to the 8 over 1. You might not want to write that over 1. And you can see here that there are no unknowns up in the exponent, so we can just work this through on a calculator. 1, 2, 3, 0.94. Ooh, 0.94. Always good to show a leading zero, hey? 0.94 to the power of 8. We get 6,705. That's the projected population after 8 years. And I'll give my units, they're people. Okay, last couple of word problems. This one is a compound interest problem. How do I know? It uses the word compounded. So here's my compound interest formula. P means something different here. P means the principal, or the initial amount. A means the amount after some time. R is the nominal interest rate, or the one that's posted. N is the number of compounding periods per year, and T is the number of years. So let's pull this apart. $15,000 investment. So that is the principal, what you start with. 6% interest. In this case, R is 0.06. In compound interest, you don't need to do any extra stuff to figure out what you add or subtract. It's all in the formula. It's compounded monthly. That means that it happens 12 times per year, so n is 12. Find the value of the investment after 5 years. So let's plug all this in. A equals 15,000. 1 plus 0.06 over 12 to the power of n is 12, t is 5. Okay, that 5 years was t. The only thing that I would do here before throwing it in my calculator would be the 12 times 5 in my head. I'd call that 60. Okay, otherwise, you may run into issues in how you input it in your calculator. So 15,000 times 1 plus 0.06 divided by 12. Okay, and this is all to the power of, I'm going to use brackets just to be paranoid. If I put in 5 times 12, I would really rather just put in 60 there. I put it in carefully enough that everything worked out. $20,232.75. And of course, the actual answers are in the answer key and worked solutions as well. All right, after how long will the investment be worth $25,000? Present your final answer in years. So, in this case, we know the final amount is $25,000, the A. We know the initial amount is $15,000. We know that the nominal interest rate has not changed. It's still monthly. So this will be to the power of 12t. The number of years is unknown. So what I'm going to do here first, I know I'm going to need logs eventually, but not yet. To start with, I'm just going to divide this out. Now, of course, all these zeros divide out. 25 over 15 reduces to 5/3, so I'm just going to write it that way. You don't have to if you don't want to. I also find at this stage that if you can, sometimes people like to actually figure out what's going on in that bracket and write it just as a number. So 0.06 divided by 12 is going to give us 0.005, so I can rewrite this in this way. You could figure that out in your calculator like this. 1 plus 0.06 divided by 12. Hey, yo, there it is. Now it just looks a little less daunting to me, so I think that's a win. I'm going to log both sides because I want to get that t down there. Some of you are going to want to bring down the exponent right away. That's fine. So I have log of 5/3 equals 12t log 1.005. Still working on getting t on its own. I'm going to do it in 2 steps. You can do it in 1 if you want. Just nervous about calculator input errors. Okay? And I know that'll be my fault. It's my fault for not telling the calculator something clear enough. But I'm just going to put it in a little more safely by going log 5/3. Ooh, I had an extra bracket there. Let's do that again. Log 5/3 divided by the log of 1.005. This is exactly what's shown on the page. So get 102.4. I'm only going to write 102.4, but I'm going to keep all those decimal places in there in my calculator because I know the last step is divide by 12. So let's go to the calculator and do that. Just take the answer, divide it by 12. Get 8.53 years, or 54. $8.54 years. Okay, or you could say just about 8.5 years. I think in the answer key I show this one a little bit differently because I'm using a different compound interest formula where n means the number of compounding periods that happens in the whole lifetime of the investment. but this would be a little closer to what we've done in class this year. All right, lastly, PET scanning, positron emission tomography, uses isotopes with short half-lives, such as fluorine-18, which has a half-life of 110 minutes. Suppose a 500 milligram sample is set to be shipped. Write an equation for the mass of fluorine-18 that remains after t minutes. Let's check this out. So the initial amount is 500. Okay. Anytime you see half-life, we're talking about a base of a half. T is unknown here. It's the number of minutes that pass. And the actual half-life, the amount of time, that's smiley face. So T over 110. I can head to my calculator and just work that through. No, I can't. I don't have enough information yet. In part B, I can work it through. Suppose the sample is shipped on a 3-hour flight. How much fluorine-18 will arrive at the destination? So this is pretty wild. Less of it will arrive at the destination than was shipped because it is decaying. 3-hour flight, and the only thing I need to be careful of here is that 3 hours is 180 minutes. I want to work in a consistent unit of time. Doesn't matter what that unit is, but since smiley face was in minutes, let's do t in minutes. All right, so we have 500 times a half to the power of 180 over 110. Just plug and chug in the calculator. 1/2 to the power of, careful here, extra brackets. Otherwise, it'll go to the power of 180, evaluate that, and then just divide your answer by 110. So I've got extra brackets happening up in my exponent, and I get 160.83, or about 161. Okay, roughly 161 milligrams. After how many minutes will the sample be reduced to 10 milligrams? So let's take this equation that's up here and put in 10 for P. And we get T over 110. First thing I'll do here is try and isolate my exponential term. So I'll divide by 500. That'll get me 1 over 50 equals 1/2 to the T over 110. Next thing I'll do is take the log of both sides. So log of 1/50th, which you can call 0.02 if you want, equals the log of 1/2 to the T over 110. Use some log magic. So I can pull this exponent down front. Get T over 110, log of 1/2. Now for me, I want to divide out right now. I want to divide out my logs. So divide by log 1/2. And what's happening here, we're not canceling out logs. We're taking the log of 1/50th and dividing it by the log of 1/2. On the right-hand side, yes, they do divide out. So log of 1 over 50 divided by the log of 1 over 2. You get this 5.64385561 number. I'm just going to write a couple of those digits down, but I am going to keep the rest of them. So T over 110 equals 5.64-ish. And now I'm just going to multiply by 110 to get T on its own. Okay, we get 621-ish. You might think, oh, that's a long time. But remember that the units here are minutes. So it's a little over 10 hours. All right, that gets us through all the questions that are on this review. I hope you found this helpful. Again, there are links in the video description for the Chapter 8 Concept Roundup, for the PDF of this review, as well as its worked solutions. And you can also find timestamps of all the different questions that are in here.